All right then. Hello. My name is Eric Wilson. I'm at Texas Southern University, and tonight I'm going to go over um how to get a solenoid field from Biot-Savart's Law. The reference is Griffiths, Introduction to Electrodynamics, third edition, from Princess Hall. Um, so, uh, we're going to use the fundamental formula for finding a magnetic field due to current with the Biot-Savart's law, and we're going to work out this problem real fast. So the the problem is 544 to find the field inside and outside an infinitely long solenoid of radius r with n turns per unit length carrying a steady current I. And that is the problem. So um, I'm going to write the law up on the board here. Uh, Hopefully you can see it. I'll bring the board a little closer. Okay. So the law is this side. It's easier. So as you can see, it's the magnetic field is equal to mu naught over 4 pi, the integral of k cross um, the radius and radius prime minus radius prime over the absolute value of radius minus radius prime, integrated in a small increment here, dA prime. And where K is the surface current density uh, for a solenoid with n turns per unit length carrying a current I. And K actually equals I. So we're going to just use this problem in rectangular coordinates for now. It's natural to use cylindrical, but we can convert it later on. So a source point R prime lies on the solenoid. So if the radius of the solenoid is R, then papers and stuff. If the solenoid radius is R, then R prime equals just these coordinates here. And this is just R prime equals to um, x, y, and z in their unit vectors. Um, and of course, you have x squared plus y squared equals r squared, big R squared. And then, of course, we have vector r. In this case, we'll have it equal to r and the unit vector of x. So, putting all this together, we'll do so the vector r minus vector r prime is going to equal hang on a second. Pretty abstract stuff. So it's going to be equal to r minus x, unit vector of x, plus y and z in their unit vectors. So I hope you can see this. From the symmetry of the setup, we replace z by negative z in the source point of r prime. K remains unchanged, but the x and y components of k cross, let me write this down, k cross r minus r prime they're going to change sign. So the components are going to cancel out, and the net field must lie in the z direction. So we're going to restrict our attention to that from now on. Okay. So we'll do that. Hang on a second. I'm trying to do a couple things at the same time. So here's our conversion over to the cylindrical coordinates. So x, of course, equals r cosine phi. Y equals, we'll put big R sine phi, and instead of just z, we're going to use the dA prime is equal to r d phi dz. Alright. So we're going to put all of this in the Biot-Savart Law. So we're going to get this messy looking double integral, and it's going to be really awful, but that's okay. We can handle it. it's hard to read. This is from 2 pi, 0 to 2 pi, the first part. Second part, from positive infinity, well, negative infinity to positive infinity. And all this has r sine squared phi plus cosine squared phi. I hope you can see that. Minus, let me turn this board, and it might be easier to see. I'll rewrite it. This is going to be a little longer than 5 minutes, unfortunately. This problem is not an easy problem. So I'm going to set this up right where you can see it. Hang on a second. Let me pause this real fast. Okay, back to where we were. So I'm going to write this equation out really fast. Hopefully you can see it. So, hang on a second. It's looking like this is coming out. Alright, here we go. So the magnetic field equals mu number of turns times the current all over 4 pi, and we have this nasty integral from pi 0 to 2 pi, and from negative infinity to positive infinity, and then we have r times big R times sine squared phi plus cosine squared phi times or minus r cosine phi. All this is over r minus x squared plus y squared plus z squared all to the 3 halves. And this is integrated over r d phi. Actually, in this case, we're going to swap around our units a little bit here to make things a little easier. R dz d phi. So, and this can be simplified a bit, quite a bit. So I'll do that. Actually, I already did that, but I'm not going to write all the steps out. I want you to be able to see it. This reduces to r squared minus little r times big R cosine phi dz d phi all over big R squared plus little r squared minus 2r big R cosine phi plus z squared to the 3/2. So that's not really much of a reduction, and it's very unlikely that I'm going to be able to do this integral by hand. So for the benefit of brevity, we've put this through Maple 14, and it spits out some results. So, but before we do that, I'll rewrite this. At this point, you have to do the integrals in the right order. Can't do the phi integral first because these are elliptic functions, which really the math is a bit beyond me because I haven't learned that yet. That's graduate work, but here we go. It's kind of neat that this book does go cover this stuff. Basically, end up with an integral that looks like this. Rewriting this thing, this monstrosity. Took a lot of time to do, but we're going to do it in just a second. Sorry, Dr. Storer, I'm going over 5 minutes here, but this is kind of a long problem. Well, not really that long, I guess. And I've never done this before. Video thing with my computer before. Okay, so magnetic field is equal to 2 mu naught times the turns times the current over 4 pi unit vector z hat from it integrates from 0 to 2 pi. You have big R squared minus little r times big R cosine phi divided by big R squared plus little r squared minus 2 little r big R cosine phi. And this is all with respect to d phi. Or, yeah. Using software, this integral comes out to two pass. You have 0 for all r, for little r greater than big R. And then you have your constant that's left over. The mu naught, the turns, times the current. Times the unit vector of z. So, there it is. This was problem 544. I hope you enjoyed the video. Thank you. Good night. Hang on, I'm going to move. There's a big glare across the screen from the light. So I'll rewrite what I wrote down over here. Hopefully you'll see it. This will be mu naught turns current unit vector z. Okay, so this is for little r less than big R. This one right here. Okay. That should clear things up.